All right, sir. This idea of force, first of all, how would you define force? Hmm. So, for example, definition. Okay. The first thing would be it's either a push or a pull, push or pull. One way to define force. Another way to define force is an agent which causes to change state of motion. State of motion. Okay. That means that if an object is at rest, it can make it come into motion. If an object is already moving, it can cause the object to slow down or to stop, or if it's moving with a certain velocity, to change the speed of the object, right? That is what a force does. Okay, now in order to calculate force, we have got formulas. There are two main formulas that we use. So, formulas. Okay, two main ones are F is equal to ma and F is equal to delta P by delta T. Okay, both are in a way the same formula. I can derive one from the other, but and I'll show the derivation of how one it can prove to be the same as the other. Acha, so for the first one, I know force is equal to mass times acceleration. For the second one, I know that this is equal to a rate of change of momentum. So delta P is change in momentum. Delta T is how that happens over a period of time. So delta P by delta P would be rate of change of momentum or change of momentum over time. So this first formula is interesting. It is saying that F is equal to ma, or force is mass times acceleration. So we can make two deductions from it. First, if we apply force on an object, if we apply force, that would create acceleration. If we apply force, what it does is it creates acceleration in the object. Apply force, this creates acceleration. Acha, sir, this is not always 100% true. Why? Because we would soon see there are cases when we apply force, but then that force is nullified by some other force. Let the azan finish and then I'll continue with my explanation. All right. So, sir, this one we can make a slightly better statement if we say if we apply net force on the object, or if net force on the object has some value, it's not zero. So then we would know that the object would experience acceleration. And why we have used the term net force, I'd tell you in a bit. Okay. So the other way of looking at the same statement F is equal to ma is that if an object is experiencing acceleration, so for accelerating objects, I can tell one thing with certainty. No object would accelerate unless some net force is acting on the object. Okay, net force acting on it. So in a way, these are two sides of the same coin. Understood, sir? Okay, sir, for other than formula, we can calculate forces by mere addition and subtraction. So for example, for multiple forces, if I have got multiple forces, so for example, if I'm applying here is a point object, so I am applying a force of 5 Newton this way and 5 Newton the opposite way. So now I will calculate what I call net force. So this one is F1, this one is F2. So F1 is equal, sorry, net force is equal to F1 plus minus F2. Why? Because force is a vector quantity. If I'm taking the rightward forces as positive, I'll have to take the leftward forces as negative. Okay, so I'll get sigma F is 0 in this case. The forces they balance out. So net force is 0. So for this object, one can say that you were applying force on this object, but would this object experience acceleration? No. Why? Because net force is not positive, net force is 0. Okay, so if there is a net force which is acting on the object, that would create acceleration. If forces, multiple forces are acting on the object which are nullified, which makes the net force as 0, in that case the object won't accelerate. Okay, so another scenario could be that you have got same 5 Newton acting towards the right, F1, on a point object, and then you have got 7 Newton acting leftwards. This is F2. Okay, so now if I calculate the net force, it will be equal to 5 minus 7, which is equal to minus 2 Newton. Okay, and in this case, the object would accelerate. Understood, sir? In the first case, it won't accelerate. Okay, sir, let's move on to no discussion on force is complete without a reference to Newton's laws. So, Sir Isaac Newton suggested three laws concerning forces. The first one is what we call law of inertia. Okay, do we remember what this law is? In one simple statement, objects tend to continue their state of motion. Okay, so this means that if an object is at rest, its state of motion is that it's at rest, it has got no motion, it would tend to continue that way. So for example, the table which is lying over here in front of me, it would continue lying over here at rest unless some force comes along and makes it move. Okay, so without application of any force, the objects, their natural state is that they would tend to continue the state of motion. Similarly, if a particle or a car or any body, it was moving with a constant velocity, it would tend to continue moving with that constant velocity. It would tend to continue moving with that constant velocity until some force comes and changes that velocity. Okay, so this is your law of inertia. So the second law is about acceleration, that the acceleration which is created in the body, it is dependent on two things. First of all, acceleration is directly proportional to force. The greater the force that I apply on the body, the greater the acceleration that I'd create in this body. And similarly, this acceleration, it would be inversely proportional to mass of the body. So if I'm applying a constant force on two bodies, the one with lesser mass would accelerate more, the one with greater mass would accelerate less, right? So combining these two, I get A is directly proportional to F by M. A is equal to, I introduce a constant K, which is equal to 1 F by M. I say K is equal to 1, therefore A is equal to F by M, and eventually I get F is equal to MA, the equation that I use throughout my syllabus for calculation of force. Understood the second law? So this was the second law. All right. Sir, the third law is that for every force that acts, there would be an equal and opposite reaction. Hmm. Hmm. For an object at rest, if an object is at rest and I apply some force on it and it continues to stay at rest, the object doesn't move. Could be the case. So, for example, if I have to push a car, I start applying the force on the car and the car doesn't accelerate. So, I go back to my physics books and say that all my life has been a lie. I was told that whenever I apply a force, it would create acceleration. No. If an object is staying at rest while you apply force on it, the reason is that the object is applying an equal and opposite force back on you, which makes the net force zero. So for force, there could be equal and opposite reaction. This is your third law of forces suggested by Newton. Okay, sir. Now, having gone through it, the next thing that we have to see is, and this is a whole new world. With forces, there are certain related quantities. All right, sir. What are the related quantities that we have got? Sir, first of all, let's see. Hmm. Let's see the first quantity that we have got, which is what we call weight. Right, sir? Not exactly a related quantity. Weight is force in itself. Weight is no different from force. How? The difference between weight and mass. So there are two related quantities. There is weight and then there is mass. So how do the two correlate? I've got W is equal to mg. Okay. So where g is acceleration due to gravity, which has a precise value of 9.81, and sometimes we are told to round off the value to use the value of 10, but we know the precise value would be 9.81. Okay. So if I were to quickly give difference between mass and weight, mass would be quantity of matter in a body. Quantity of matter, right? Whereas the weight is the force with which, hmm, G. I'll show in this. So F is equal to ma. When a body is experiencing the acceleration of gravity, the force that it experiences is the weight. Okay. So force with which the earth attracts anything towards its center. Okay. So go ahead. The phenomena of a mass experiencing acceleration towards the earth with the value g, that is the earth. Sorry, that is the weight. Okay. And then, sir, we would know the difference in terms of unit. The unit for mass is kg, and the unit for weight is newtons. Why? Because it's a force. Understood, sir? So this was the first quantity. Go ahead. Hmm. No, weight is also in newtons. Meter per second squared. Okay. Hmm. A good point. Good point. Acha, this I could have mentioned above as well. See, uh, what is the unit of force? So if I go for SI unit, the unit for mass is kg. The unit for acceleration is meters per second squared. So I can give force in terms of kg meter per second squared. Okay. And that would be the unit of force in terms of base units. In A levels, you get these questions quite often that you're given a quantity and you're asked to calculate the base unit. So you'll have to calculate the unit of that quantity in terms of the units of those seven fundamental quantities that we have discussed before. Okay. So this is the unit of weight. Sorry, this is the unit of force in terms of base units, but the unit that we use more often is a Newton. Okay, so 1 Newton is 1 kg of mass experiencing an acceleration of 1 meter per second squared. Okay, so this was the first quantity. Another related quantity is we say momentum. Okay, what is momentum exactly? Momentum is described as quantity of motion in a body. So quantity of motion in a body is called momentum. It is given by the symbol P and is calculated mass times velocity. Okay, this is the formula for it. Okay, and then the unit. So momentum unit for mass is kg. The unit for velocity is meter per second. So we usually use the unit kg meter per second, but there is another unit that we'll soon learn about. We use that one too. Okay. Sure. Sir, from momentum, how is you would ask that how is momentum related to force? As I said, how is it a related quantity? Let's see. Sir, for momentum, we have got a phenomena if there is change in momentum. Okay, so that would mean the body, it had a later momentum P2 and an initial momentum P1. So momentum changes from P1 to P2. So if I subtract the two, I'll get change in momentum. Agreed? Okay. Sir, usually we use the symbol V for final velocity, and we use the symbol U for initial velocity. Okay. So the momentum would be mv minus mu. Yes, delta p. Sir, I can say delta p is equal to m times v minus u. Sure. By the way, sir, this phenomena of change in momentum, this is called impulse. The change of momentum of a body is called impulse. Come again, sir. Unit for gravity? Hmm. Sir, gravity, if we are talking about force of gravity, then it would be Newton. If we are talking about acceleration due to gravity, then it would be meter per second squared. Later on, you would see gravitational potential energy. So for that, unit would be joules. Newton per kg. That would be the same as acceleration due to gravity. See, good question. Okay, so I have got W is equal to mg. If I make g the subject, I get W over m is equal to g. The unit for weight is newtons. The unit for mass is kg. So that is also what you would learn later on in A levels called gravitational field strength. Okay. The force that an object experiences per unit mass. That is gravitational field strength. So that would be Newton per kg. And it's the same as this value g, acceleration due to gravity. Understood? Okay. So we were talking about impulse. I said delta p is equal to mv minus mu. So sir, if I divide both sides by t, so this change in momentum, obviously it would happen over a period of time. So if I want to see how rapidly it is happening, what is the change happening per unit time, it becomes delta p by delta t is equal to m v minus u by delta t. Yes, and v minus u by delta t, this is equal to acceleration. So I get mass times acceleration is equal to delta p by delta t. And we just learned, just a second, mass times acceleration is force. So force is equal to delta p by delta t. Yes, sir, you were saying? Momentum equals force over time. No, no, no. Just a second. Okay. For that, if you could just wait for 1 second. So, sir, for this final formula, I can say that force is one way of defining force is rate of change of momentum. Rate of change of momentum, or I can say it is a rate of impulse. Why? Because change of momentum is called impulse. So I can also call it rate of impulse. Okay. And now if I further rearrange this formula, I get delta P is equal to force multiplied by time. Okay, so that means the impulse, which is change of momentum, can be calculated two ways. Either I do P2 minus P1 or delta P, or I do force multiplied by time. Both of them will give me calculation of impulse. Okay, so if I go by the first method, delta P by delta P, so change of momentum, the unit for impulse, I can see it is kg meter per second. If I go by the second formula, I will get, okay, so the last formula, it gives me F into T, which is Newton second. Okay. Also, on a side note, if I further want to see that Newton was equal to kg meter per second squared, if I multiply it with second, so this is force multiplied by time. So yes, I get kg meter per second. Okay, so in any case, this is your unit, base unit, and this is your regular unit for impulse. Understood? Now, what were you asking? Is the question addressed this thing you were asking, that change of momentum is equal to force multiplied by time? I thought you was hmm, hmm. So if I multiply both sides with time, I get change of momentum is equal to force into time. Okay, so I multiply both sides with time. Force times is equal to impulse, change of momentum. Hmm. And impulse is also equal to force multiplied by time. Okay. The formula for impulse is, you can use both the formulas, by the way. You can use F times T, or you can use the other one, P2 minus P1. Understood, sir? Any confusion about it? Hmm. Hmm. Mm, correct. It's the same for both of them. Hmm. Understood. Okay. So, sir, the next related quantity that we have to see with regards to force is that if this force is being applied on a spring to stretch it. Okay. So the first one that we did was weight. The second that we did was momentum. The next that we are going to see is in case of a spring, what would happen? Okay, so in case of a spring, so sir, the force that we apply on a spring causes it to stretch or compress. Yes. So we get F is directly proportional to negative X. So this is the restoring force in the spring. So for example, if I stretch the spring, so I stretch a spring, the restoring force would act in the opposite direction, right, towards the center. And if I compress the spring, the restoring force would be outwards away from the central position of the spring. So this negative sign, it just shows that the restoring force, it is opposite to the direction in which the spring is stretched or compressed. And sir, then I can say F is equal to negative kx, where k is spring constant. Okay. And this can further be rearranged as, if I ignore the negative sign, F by x is equal to k. Okay. And this would be a constant value for a given spring. It's inherent property of a spring. Okay. The same way density is an inherent property of a spring. You will later learn about resistivity, that is inherent property. So all these values, as long as the spring is made of the same material, it is going to have the same spring constant. And the unit for spring constant would be Newton per meter, right? Written this way or this way. All right. Sir, if I were to draw a graph where I have force on x-axis and extension on y-axis, I would get a straight line which would then turn. So, sir, this point before this straight line, this starts to turn. This is called, okay. So, sir, this point after which the spring it stops obeying this Hooke's law. By the way, this law is called Hooke's law. Stretch or compressions. In fact, so Hooke's law is that the extension or compression experienced by a spring is directly proportional to the force applied on it. Hmm. Or you could say that the restoring force created in a spring is directly proportional to the extension or compression of a spring. So the more it is stretched or compressed within the limit of elasticity, within the limit of proportionality, the greater the restoring force would be. But once the limit of proportionality or limit of elasticity is breached, then the spring no longer obeys Hooke's law. Then it won't be the case. Go ahead. Hmm. So sir, for this one, if we see what is the gradient of this line, gradient is delta x by delta f, right? Because delta y by delta x is gradient. So this is equal to 1 over k, right? So if the force extension graph is drawn this way with force on x-axis and extension on y-axis, the gradient would be 1 over a reciprocal of spring constant. Understood, sir? All right, sir. This was another thing which was related to the concept of forces. Sir, another related concept for forces is, just a second, let me fill in the colors. Okay, all right. Sir, what we call moment. So momentum we have done. There is another quantity called moment. What is moment, sir? Sir, moment is if I have a body which is attached or made to, I've got a rigid body, okay, and it is allowed to turn about a point. So this point is called pivot, okay, and then I apply the force perpendicular to this body. It will create turning effect, okay. So the turning effect given by moment is calculated by force multiplied by perpendicular distance between the point of action of force and pivot, the point where the body is allowed to turn about. So force multiplied by perpendicular distance, you would have pivot. Understood, sir? Okay. So moment you can call turning effect in a body. Turning effect. Okay. So as for the unit, the force is measured in newtons, distance is measured in meters, so the unit for moment would be Newton meters. Understood? Okay. And so then you remember from the previous classes, we also discussed that what if this force which is creating the turning effect is not applied vertically or perpendicular to the rigid body, rather it is applied at an angle theta. Yes? So in that case, we would say that this force, it can be divided into two components. There would be a horizontal component and there would be a vertical component of this force. Yes? So only the vertical component of the force would create moment, horizontal component won't. So we said we have got Fx, the horizontal component, Fy as the vertical component. So this angle over here, this would also be theta. And using the rules for right angle triangle, I get sine theta is equal to, this is the force Fy divided by F, and the perpendicular component would be F sine theta. Okay, so in this case, moment is equal to F sine theta times d, can also be written as F times d sine theta. Okay, so So then you would remember that in the regular classes I also asked you that would this formula work if the force was applied at 90 degree, the initial case that there is a rigid body with a turning point pivot and the force is applied at 90 degrees to this point. So we discussed back then that it would equally apply the second formula in that case as well, because then I'd have theta as 90 degree and sine 90 would be 1, so it would become F times D. So this formula it applies in all cases of moment. Understood, sir? Hmm. Hmm. Okay. Sir, then we said that there is this thing called equilibrium. Okay. So for a body to be in equilibrium, it must meet two conditions. The first condition for equilibrium is that net force on the body should be equal to zero. We're not saying that there shouldn't be any force acting on the body. There could be multiple, one or more, not one, more forces acting on the body. But if the net sum of all those forces is zero, then the first condition of equilibrium is met. Okay, so this is the first condition of equilibrium. The second condition of equilibrium is that net moment of the body should be zero. Net moment should be equal to zero. Okay, and this is now what we are going to discuss. What do we mean by net moment of the body? So sir, a body can have moment two ways. So the same body that we discussed before, the moment that was being created in that case, it was anti-clockwise. And had this force been acting from top to bottom on this body, then the moment created in the body would have been clockwise. Agreed? So the moment is either anti-clockwise or clockwise. Just a minute, please. Good. All right. So, sir, we say that net moment hmm, we say net moment is equal to zero if sum of clockwise moments is equal to sum of anticlockwise moments. Okay. What do we mean by that? Clockwise moments, anticlockwise moments. I missed a key over here. Okay. And similarly over here, clockwise and anticlockwise. Sir, let's assume there is this seesaw, which is a rigid body. Okay. And now on this seesaw, there is one child sitting over here with his downward weight W1. Okay, so this first kid has weight W1 and is sitting at a distance D1 from pivot. Okay, and then you have the second kid whose weight is W2, and this kid is sitting at a distance D2 from the pivot. And obviously we'd have someone on the other side as well. This side you have one sitting really close to pivot W3. Okay, and then there is this last one sitting over here W4. And the distance of this one from pivot is D4. Okay, so now sir, these two W1 and W2 will create clockwise moment. Moment created by the first kid will be equal to W1 times D1. This is moment of one boy. Moment created by the other boy, W2 times D2. Okay. And if the seesaw is turning neither clockwise nor anti-clockwise, it would mean this is balanced by the moments of the kids on the other side. It would be W3 times D3 plus the other anti-clockwise moment, which is W4 times D4. Understood, sir? This is also so not net momentum, net moment. If a body has momentum, it could still be in equilibrium. Very good question. And you will tell me what's the other condition that should be fulfilled. If a body is in, if a body has momentum, how can it still be in equilibrium? Go ahead and tell me. Go on. Okay, so okay, so if a body has momentum, it means the body is moving. Okay, the condition for equilibrium is that net force should be zero, which means delta P by delta T should be zero, which means delta P should be zero, which means that momentum must not have been changing for this body, or in other words, the body is moving at constant velocity. Because momentum changes, naturally we would assume that as a body is moving, its mass does not change. So if here it is mv2 and here it is mv1, as long as mass is the same, it's only the change of velocity which causes the change in momentum. So despite having momentum, can it still be in equilibrium? Yes. Why? Because change in momentum should be zero. So it must be that the body can have momentum, but the momentum should remain constant then. As long as momentum is constant, delta P would be zero, which means rate of change of momentum would be zero, which means net force on the body would be zero. Okay. Did I answer your question? Okay. Acha, sir, one thing which I think I skipped about momentum. So another thing to keep in mind is that we would remember the difference between momentum and moment. Yes. So you have got moment and you have got momentum. Acha, sir, for momentum, we have one thing which could be tested, and that is law of conservation of momentum. Law of conservation of momentum. Okay, what's this law of conservation of momentum? Sir, this law of conservation of momentum says if there are two bodies colliding, okay, if two bodies collide, then total momentum before collision is equal to total momentum after collision. Okay. So, sir, if I were to draw a case example for this one, so here are your two bodies, M1 moving with a velocity U1. It goes on and collides with M2 moving with velocity U2. Okay. So this is before collision. And after collision, the velocities would change. So M1 moves with velocity V1, same direction, and M2 moves with velocity V2. Okay, so total momentum before collision would be the sum of momentum for each of the two balls. Yes, how do I calculate that? Just a second. Okay, so sir, that would be M1 U1 for the first body plus M2 U2 for the second body. So this is your total momentum before collision. This will be equal to total momentum after collision, which would be M1 V1 plus M2 V2. Okay, all right. Sir, one thing to always keep in mind for momentum question is be mindful of directions. Be mindful of direction because change in direction would mean that the sign of momentum or the sign of velocity would change. Okay, so just to give you one quick example on this, if a body goes and so there is a ball M1, sorry, simply M, there's just one ball. Okay, it goes with the velocity U, hits the ball, and comes back, bounces back with an with a velocity v. Okay, so if I wanted to calculate change in momentum, this will be equal to P2 minus P1. Yes, what is P2? mv. What is p1? mu. But sir, in this, one thing that I am missing is that if I am taking the leftward velocity as positive, I will have to take the rightward velocity as negative. Okay. So I could have taken the rightward as positive and leftward as negative, but the point is that if velocity in one direction is positive, the velocity in the other direction must be negative. So this would become minus mu, and resultantly the change in momentum would be mv plus mu. And this is because the change in momentum, while it happened, the direction of velocity changed. Therefore, the equation of change of momentum from minus it became plus. Understood, sir? So this is what you have to keep in mind for all questions of momentum, whether related to conservation of momentum or related to regular change of momentum or otherwise calculation of momentum. So we keep till here for today, and inshallah in the next class we would, the next week, obviously one class would be for revision and one class would be for practice of past papers. So for the revision class we would carry forward from here. All right, so see you next week.